Progress. So yeah, so I'm going to tell you about sort of a different sort of idea from what we were hearing about yesterday. The idea of how well do we know that atoms are neutral, and we'll talk about how to use atom interferometry to test that, hopefully a lot better. So first, just some brief motivation. I don't want to spend too much time on this. I got way too much I want to tell you, but sort of, if you think about the fact that protons and electrons seem to have equal and opposite charge, it's surprising in some sense. If you think the proton, it's made up, it's a composite particle made up of quarks. Electrons are these point-like leptons, and yet their charges seem to be equal and opposite. And so that sort of suggests a striking symmetry in nature between, let's say, quarks and leptons. And one thing we've learned in physics is if there are symmetries that we think we believe in, we shouldn't assume them. We should test them rigorously, right? And so that's sort of the spirit of this. And there's an interesting history of this, which I don't have time to go into. But let's just say that if you were to see a violation of charge neutrality, it would have serious implications for theories beyond the standard model, which in some cases predict an exact equality or exact symmetry here, unlike the standard model. So it would be sort of a no-go theorem in that sense. So that's kind of a theoretical motivation for this. I'm going to give you sort of an experimentalist's take as well. So the current limits on charge neutrality, so the equality of the proton and the electron, is part in 10 to the 21. That's how well we know that electrons and protons are equal and opposite. And this is really set by a series of classical tests. You can essentially think about apply an electric field, look for a deflection kind of thing. And so the best limits are set by actually, they make an acoustic resonator with gas inside, and you apply an oscillating electric field, and you look for sound waves generated by the force on a possibly non-neutral gas atom or molecule due to such a charge imbalance. That's at a part in 10 to the 21. And so it turns out, with even conservative estimates, I mean sort of honestly conservative estimates for what we could do with an atom interferometric approach, we can put 2 or 3 orders of magnitude better limits on this. And so even if the motivation is sort of, I'm not sure how many theories might predict this, if you have the opportunity to do a factor of 1,000 better and even, asymptotically much better than that, it's worth trying, is what I would say. So, and in particular, some of the systematic errors you encounter in a classical test, if you think about you're trying to drive a neutral atom with an electric field, so there's no charge, so in principle you would expect it not to deflect. There are second-order effects, that you can polarize the gas, and that polarizability can lead to systematic effects that you have to think about. And so one of the advantages we have using quantum sensing techniques is we can do things like the Aharonov-Bohm effect. So I'm going to tell you a little bit about the Aharonov-Bohm effect, which is a sort of a famous idea that it's possible to get a phase shift in an interferometric experiment, even if a particle doesn't see any classical forces. Okay, and so the famous version of the Aharonov-Bohm experiment is shown in this top figure here. So you think about an electron interferometer, where you take an electron, you split it along 2 paths, upper and lower, and we've got this red solenoid going up through the middle of the 2 paths. So the electron kind of goes around the solenoid. And if this is an infinite solenoid, there's a magnetic field inside the solenoid, but the magnetic field outside is 0. We know from sort of classical electromagnetism. And so there would be no classical force QV cross B on this electron, you would say. And yet, quantum mechanically, it turns out the vector potential outside that the electron sees results in a phase shift. So you take the line integral of A dot dl around this loop that the electron passes, and that will actually change the interference pattern. So this is sometimes called the vector Aharonov-Bohm effect because it involves the vector potential A. And there's sort of a somewhat less famous version of this, which we call the scalar Aharonov-Bohm effect. So here the idea is you take an electron and you split its wave function into sort of a lower path and an upper path, and you have these 2 blue hollow cylinders. Okay, these are just conducting tubes. They're empty, and you let the electron go deep inside before you do anything, so it's well inside these conductors. And once it is, then you apply a potential difference. You connect it to a power supply, so that you have a higher potential here than there, for example. And so since you're deep inside this electrode, the potential inside is very uniform. The electron sees a very small field because it sees a very small potential gradient. So there's, once again, a force-free condition. And yet, the potential energy difference between these two can be non-zero, right? Charge times potential difference. And so then you get a phase shift proportional to the difference in the potential energy along those 2 paths. And so we call this the scalar Aharonov-Bohm effect because it has the scalar potential phi in it. And so it turns out these are manifestations of the same effect. You can write this in a Lorentz invariant way using the vector 4 potential A mu. And in general, you can also think about these using Stokes' theorem as the phase shift arising from the flux of the field tensor through the enclosed spacetime area. So this is And we've seen the vector Aharonov-Bohm effect in experiments. This is a well-established phenomena. The scalar Aharonov-Bohm effect, harder to do experimentally, but once again, via this expression, you absolutely expect the two have to be there. If you have one, you have to have the other for things to be Lorentz invariant. So in this experiment that I'll tell you about, we're going to be using the scalar Aharonov-Bohm effect to look for deviations in charge neutrality by putting neutral atoms inside electrodes and applying a potential difference. That's sort of the essence of the experiment. And so to do that, we're going to be using this technique, atom interferometry, which is what my group focuses on. And so this is just a one-slide introduction to how we run these experiments. You have a cloud of atoms shown as this blue ball. We typically launch it vertically inside a vacuum chamber. And while the atom is in free fall, we divide its wave function quantum mechanically using a light pulse. So we can split the atom's wave function using a light pulse, acts like a beam splitter. So you have a lower path here and then an upper path. And basically this comes from the fact that you can kick the atom with a photon and you can put it in a superposition of a path that didn't get a kick and a path that did. And so we can split the atom's wave function into two paths, which is what you need to do this Aharonov-Bohm experiment, like we did with the electron. And in fact, you can get really macroscopic splittings here. So if you look at so this is versus time here. So if you look at this midpoint time here, the lower path and the upper path are separated by some distance z. And this is a picture of some rubidium atoms where we took a picture of the state at this midpoint, and the two halves of this rubidium ensemble are in a superposition separated by about ½ a meter in that case. So we can transfer enough momentum and let it separate for long enough that we can get sort of macroscopic superposition, macroscopic distance between these two wave packets. And so that's exactly what we want to do. Now we want to apply a potential for this one that's different from the potential for that one and look to see if there's a phase shift. Okay, so here's then the cartoon of the experiment. We're going to run an atom interferometer. So this is, once again, space versus time. I do a beam splitter. I have an upper path and a lower path that separate. And once they're separated, we can have the two halves of the atom's wave function shown here as these two colored balls here inside two different electrodes. So we're going to have a cylindrical electrode at potential V, and then a symmetric one below at potential minus V. And so since these two halves of the atom are at different electric potential, you would get a phase shift if there's a charge. So if it's neutral, there's no energy shift, but if the atom had some epsilon charge, then you would expect epsilon times delta V to be an energy difference times time. And so here, typically the way this is parametrized is in terms of this parameter eta, which is the sort of extra charge per nucleon, where A is the number of nucleons, would be 88 for strontium that we're using, for example. And so, as I said, the current limit's part in 10 to the minus 21 is the current limit on eta. And so just to give you a sense of, well, like I said, with relatively conservative numbers from our perspective, so spend 100 milliseconds inside the electrodes, turn them up to 10 kilovolts with sort of 10 milliradian per shot resolution, so not really pushing too hard on the sort of shot noise limit of the atoms, we can get basically 4 × 10⁻23 per shot on eta, and so which is a couple orders of magnitude better, and with sort of reasonable averaging time, average over 1,000 shots, you can get down to sort of 1,000 times better than the current limit. And I think I'm being very conservative here. We want to obviously spend a lot of time understanding systematic errors, but we could imagine integrating down for longer, turning up the voltage, having better phase resolution. So there's actually a lot of room for growth here. But right off the bat, I think per shot you're already beating the current limits. Okay, so. Now, the hardest part of this experiment is you got to get the two halves of the atom inside the electrodes. But that's something, as I showed, we've done with rubidium. The electrodes in our experiment that we're building have a separation of only a couple centimeters, but you want to be deep inside, and so you want sort of ideally tens of centimeters of wave packet separation, which, as I'll try to convince you, is something, once again, we're comfortable projecting towards. Right? We've done, I would say, 54 centimeters with rubidium, and so we can do something similar with strontium. So, for example, with 100 photons worth of momentum transfer during our beam splitter process in a few hundred milliseconds, we can get sort of these tens of centimeter separations. And so I'll give you sort of a one-slide version of how we do these large momentum transfer operations, where we transfer these hundreds of photons that we need to split the atom. I could give a whole talk on this. This is sort of what my group does on a day-by-day basis. But the real takeaway from this busy slide is that if you look here at our interferometer performance, quantified in terms of the visibility of our interferometer fringe, versus the number of photons that we've used to split the wave function into two paths, you can see that at 100 h bar k of momentum transfer to the atom, we still have over 60% contrast in the interferometer. So we sort of have robust performance, even out to a couple hundred h bar k, where we still have about 40% contrast. So and so we can use this this beam splitter operation to get that hundreds of photons of momentum difference. We've even pushed it out to 600 h-bar k, and in the near future, we're projecting 1,000 is sort of within striking distance. So, but we don't have to even go that far. Even with about 100 h-bar k, a few hundred milliseconds, we can get these tens of centimeter separations. So I think it's practical to expect to split these strontium atoms in the way we need. Okay, so we've been building this experiment, and what it looks like is this. So we've got sort of a tower, 10 meter in scale, and we're going to have one source of strontium mounted to the bottom, another one halfway up, and we're going to have the electrodes inside this vacuum chamber, which I'll show you in a second. But just generally, this tower is going to be used for multiple things. In particular, we're sort of piggybacking on this other experiment that I'm involved in called MAGES 100, which is funded by the Moore Foundation and DOE, which is building a 100-meter scale atom interferometer at Fermilab for gravitational wave detection in dark matter physics. And so this tower sort of serves as a prototype for that. And we figured while we're doing it, we should sort of build in the opportunity to do a charge neutrality test. So let's sort of zoom in on the two regions where these electrodes are over here in cross-section. So we're seeing the same tower in our lab at Stanford. And so we're actually doing two versions of this experiment, right? I showed you a picture where we had one pair of electrodes. We actually have two pairs of electrodes, and that lets us implement a gradiometer. So we've got each of our strontium sources will have an associated electrode. And so inside the vacuum chamber, so if we zoom in here, you can see that, so this is sort of the vacuum cylinder, and then inside it are these cylindrical electrodes, about a couple meters in total length, 1.7 meters, I think. And so this is the lower electrode here, and then the upper electrode there, and there's a small sort of centimeter scale gap you can see there. And we've got some insulators here to separate things and some feed-throughs. And so by having this gradiometer, it gives you sort of a lot of control over systematics, which I'm happy to say more about. I won't say too much now in the interest of time, but I hope people ask me about systematics if you're interested. So one way we can do, though, is you can have the upper interferometer with sort of plus V, minus V, and the lower interferometer with minus V, plus V. And then if you take the phase difference, so you get a factor of 2 in signal, but you're also canceling a lot of common sort of kinematic systematic errors, things that can arise from gravity, rotations, Coriolis forces, and a number of other things. And we can do various toggles. We can change the sign of these, and that gives us a lot of control, scaling these voltages and changing their sign to explore a set of systematic errors. So this is the idea of a differential measurement between the two interferometers cancels many of our common source of noise. Okay, so as I said, I'm going somewhat fast through this, but I'm happy to address, there's lots of interesting advantages, I would say, to this differential measurement protocol for measuring, for reducing systematic errors. Okay, so we've built this. We've been working on this for the last couple of years, and so this is our CAD model once again. We've got sort of a real picture here, pretty close rendering, and so we've got some alumina insulator spacer rods here. It's about 1.7 meters end to end. And so we built this in our clean room, and then we sort of integrated inside the vacuum system. So you can see here, this is right before we installed it. So we've got this sort of chamber here with the high voltage feed-throughs. One electrode is already inside this half of the vacuum chamber. You see the other electrode here, and it's about ready to be inserted in the other half of the tower. We sort of rolled these together and bolted it all up. And then we tested it and made sure it could hold sort of 18 kilovolts and the voltage stayed consistent and didn't discharge or anything like that. So here are the fully assembled tower segments. So each of these corresponds to sort of half of our tower that we're building, one for each atom source. And inside each of these is our high voltage electrodes. You also see some magnetic shield on the outside. We've got our vacuum system. And so these two halves had to be put together. We built it into one sort of 10 meter scale instrument. You see sort of our lifting cage 80-20 structure on the outside, and then we lifted it. So we've got sort of, here's a picture midway through the lift with the chain sort of pulling it up. And then you can see the sort of happy team here after a long day's work getting this installed vertically. And so you see the tower sort of installed in the lab. And here it is sort of with all the lifting cage removed. I've got a magnetic shield. And the atom sources will be in these two locations. And that's sort of the next step is attach these atom sources. And we can start to do gradiometry and eventually then turn on these electrodes. So that's kind of the state of the experiment. Before I end, I've got sort of one sort of big important issue I want to raise, which we sort of have been thinking about for the last number of months, which is there's a possible no-go for this experiment. Sort of potential shielding effect that you've got to worry about. Okay, so I wanted to unpack this because I think it's super interesting, and I think we have a way around it. Okay, so here's the problem. The textbook scalar Aharonov-Bohm effect just assumes you apply some potential somehow, right? You just apply a potential, and then sure enough, quantum mechanics says you get a phase shift. But in practice, how do you actually apply a potential? You usually use a conductor. And of course, conductors have free charge that you don't get to control. The charge goes where it wants to go. And in particular, there are image charges. And so this is a potential shielding effect of our phase shift due to image charges. And so I want you to look at this cartoon over here for a moment. So this is a sort of a picture of our vacuum system on the outside. We've got these two gray regions, which are our electrodes. This is the upper electrode and the lower electrode. And this here, point charge Q, that's our sort of possibly charged atom. And the field lines show you sort of what's going on, right? So the field lines here all kind of terminate on the inside wall of this electrode. And so that means there's an induced surface charge on the inside of this electrode. And so now, and this was an effect first pointed out in 2015 by Wang, this nice paper, showing that if you think about the potential, or the energy rather, that this charge would have, Q times V, if this electrode is at potential plus V, you should maybe worry that the surface charge is also sitting at potential V, and it has equal and opposite charge. So there's a potential for a cancellation there, and I think it's a real cancellation, so you have to worry about that. And so in general, the way to think about this is we need to think about the net interaction energy between the particle and whatever is applying the potential. So we think we understand that now. And sort of a good resource or a good way to think about this is pointed out by this nice Weidman paper in 2012, which is that generally in Aharonov-Bohm type experiments, there tends to be an entanglement. There's generically an entanglement between the particle and whatever source you're applying it. So in this case, the electrodes and the charge actually become entangled via their interaction. For the purposes of the last 30 seconds of my talk, I'll just use this simplified version of the electrode, just because it's a little bit easier to model geometrically, where instead of these cylindrical electrodes where you can have a negligible amount of fields leaking out, we'll think about a point charge inside a spherical capacitor, or a spherical shell. So this is a conductor here. There's a spherical cavity inside. You put a point charge inside. And we all know from sort of undergraduate E&M, if you put a positive point charge in here, there will be a negative surface charge induced on the inside. And if this is a neutral conductor, there will be an equal charge plus Q distributed on the outside. And so I just want to think about the spherical geometry just to kind of make the high-level argument. And so as I claimed, the thing that matters is the interaction energy. So in fact, what you care about for the phase shift in such an interferometer is the action, the integral of the action, which depends on the Lagrangian. And in this case, the Lagrangian is the electromagnetic interaction between matter and field. And it turns out you can write that as just the electrostatic energy, U, integral of rho v 1/2. And you can also write that in terms of sort of the capacitance matrix of the system. And so I'm sort of wrapping up here, only sort of a couple more points. And so let's just sort of draw what this superposition looks like, this entangled state that I'm arguing you have to worry about. So I've got two kets here, which represent the two states once I've split my charge. So I've got electrode upper, electrode lower, and I can be either the charged atom is in the upper electrode or it's in the lower electrode. And if it is, there's going to be a minus surface charge induced on either of those electrodes. Now, if you apply a voltage, plus V and minus V, you can convince yourself actually that the energy difference between these two states is actually zero. And that's, you can just understand from the uniqueness theorem, right? It doesn't matter what's going on inside this cavity, the energy outside is independent of that. And so these actually have the same electrostatic energy, and that's sort of this effect pointed out by Wang. There's no phase shift in that case if you apply a voltage boundary condition. However, if instead of doing that, if you simply add a fixed amount of charge plus Q and minus Q, if that's your boundary condition instead, then in fact you do get a phase shift, because now the charge brought to the outside plus small q interacts with this big Q that you add. So these are actually different experiments. You either apply a voltage or you add a certain amount of charge. They're different. They have different predictions. And so we want this one. And so how do you, in principle, how do you actually implement such an experiment where you add a certain amount of charge? Maybe a hard thing to do with a power supply. And so we have sort of a simple scheme. This is where I'll end. I'll just point out how to do this. So first off, you charge up your electrodes to some common voltage V before you split your atom. So it's down here. You've got plus V and plus V. And then you just disconnect them. So you float them. So there's some amount of charge Q that you've placed on them. Now the power supply is no longer involved. It's not servoing the voltage. Now you split your atom. You split it into two halves. So now it's sort of grayed out because it's in both places at once. And in this case, you've got this entangled state where the upper electrode is Q, lower electrode is Q if the charge stays downstairs. If the charge goes upstairs, there's actually more charge upstairs and less downstairs. And in that case, you now have you can get a potential difference, or energy difference rather, if you simply ground the lower electrode. So I don't have time to go through the details because I'm way over time, but it turns out in that particular scheme, you do recover a non-zero energy difference. So, so this is, I think, a workaround for this. So there's a no-go, but we can actually get around it and make a measurement. So I think with that, I'll leave it there and thank the team, and in particular point out Rachel, Ijun, and Mahiro, who built this system and who are hanging out in the back here. And yeah, so thanks for letting me run a few minutes over.
All right, let's thank our speakers.